teardown of a data center cooling unit opened on a bench in early 2024 reveals something no spec sheet labels. Inside the variable speed compressor drive, behind the power management board, sit a set of permanent magnets whose material history the unit's manufacturer does not disclose and cannot fully trace. The surface is anodized aluminum and injection molded plastic. Underneath that is a supply chain. Underneath the supply chain is a single processing choke point, and underneath that is the structural reason this object exists in the form it does. The restriction on rare earth processing was not imposed on China's competitors from outside. It accumulated from decades of capital allocation, chemical expertise, and tolerance for environmental costs that no export control can replicate in the short term. Cut deep enough into any data center or chip fabrication tool, and you find that constraint expressed in the material properties of the magnet itself. We are going to cut from the physical hardware inward, through the magnets, through the refining process that produced them, through the industrial geography that makes that process nearly unreplicable elsewhere, until we reach the layer the teardown reports describe as a sourcing note, but which is, on closer examination, a load-bearing constraint embedded in the physics of the device itself. The cuts run from the outer shell to the deepest layer. What the teardown sees, where the material actually came from, what the processing concentration really describes, and what the constraint looks like when you measure it in steel and torque. When the variable frequency drive motor is disassembled, the permanent magnets inside are typically unlabeled by material composition. Equipment manufacturers are not required to disclose the rare earth content of subcomponents in most jurisdictions. The magnets are present, their field strength is specified on a datasheet, and their origin is not. This layer exists because the supply chain for rare earth magnets was, until recently, treated as a commodity logistics problem rather than a strategic materials question. The magnet is specified by what it does. The oxide that produced that capability is several tiers upstream and invisible to the integrator who assembled the cooling unit. The magnet assembly sitting on that bench carries a part number. It does not carry a country of refining stamp, and the integrator who installed it almost certainly never asked for one. The next layer down separates mining from processing, and it is here that the object's history begins to look different from what its supply chain documentation suggests. Rare earth mining is geographically distributed. Australia, the United States, and several nations in Africa collectively account for a meaningful share of global mine output based on geological survey data and industry estimates. Yet the separated, high-purity rare earth oxides that those ores eventually become are processed predominantly in China. The ore travels. The chemistry, by and large, does not leave. Processing rare earth ores into separated oxides requires a multi-stage solvent extraction process using large volumes of chemical reagents. It generates substantial acidic and radioactive byproduct streams. It demands years of operational refinement to achieve the separation purities that high-performance magnet alloys require. Outside China, the combination of environmental permitting timelines, capital costs, and the absence of existing operational expertise has prevented the emergence of comparable capacity. This is not a policy outcome alone. It is an infrastructure and knowledge accumulation outcome, and it predates the export control debates that have since made the supply chain visible. The magnet on the bench passed through this process. The specific refinery is unknown. The geography is statistically near certain. The third layer names what that concentration actually measures, and the number requires some care to read correctly. Independent analysts and trade flow data, which should be understood as estimates rather than audited figures, suggest that somewhere near 9/10 of global rare earth processing and refining capacity resides within China. This figure covers the full separation cascade, from ore or concentrate into individual rare earth oxides at the purities magnet alloys require. The figure for neodymium and praseodymium, the elements most relevant to high-performance permanent magnets, is believed by most analysts to be at least as concentrated, possibly more so. The 91% figure is not a market share statistic in the conventional sense. It is an industrial infrastructure description. Processing capacity of this kind is not fungible. It comprises solvent extraction cascades, roasting kilns, wastewater handling infrastructure, and decades of accumulated process chemistry. The kind of knowledge that produces consistent high-purity separation lies in the hands of operators and in undocumented process adjustments, not in patents or equipment lists. A competitor acquiring the patent portfolio tomorrow would still face a decade or more of operational learning before reaching comparable output quality. To render this in physical terms, consider what it would mean to control not the world's wheat fields but the world's flour mills, and not by owning them all, but because yours are the only ones with the full milling and sifting infrastructure, and because building a comparable mill from scratch takes a decade of construction and another decade of operational learning before the output reaches the consistency that a high-performance application requires. The wheat exists elsewhere. The flour, for now, comes from one place. The concentration is the product of deliberate industrial policy sustained across multiple decades, combined with a willingness to absorb environmental costs that made the industry uneconomical or politically untenable in other jurisdictions when the critical infrastructure decisions were being made. The result is not a cartel in the conventional sense. There is no single price-setting body, but the practical effects of structural monopoly on process capability are similar to those of a cartel in their consequences for anyone who needs the output. The magnet on the bench required flour. The mill is in Jiangxi or Inner Mongolia in all statistical likelihood. The deepest layer is visible not in trade data but in the object's own dimensions. The maximum energy product of a neodymium iron boron magnet, the number that determines how small a motor can be made while still delivering the torque a cooling compressor or a wafer positioning stage requires, is set during the oxide separation and alloying stages of refining. It is not set during the magnet's final sintering. A fabricator working from incompletely separated rare earth oxide cannot reach the same performance ceiling no matter how precise its downstream metallurgy. The spec sheet lists the output. The refinery set the limit. Lithography equipment, the class of machines that exposes circuit patterns onto wafers, uses precision linear and rotary stages whose positioning accuracy depends on the field uniformity of their drive magnets. The teardown literature on this equipment class, where it exists, consistently shows neodymium iron boron assemblies meeting specifications that require separation purities available only from fully developed rare earth processing operations. No comparable independent source has confirmed that a high-throughput alternative magnet chemistry, whether samarium cobalt, ferrite, or electromagnet-based alternatives, has been substituted at scale in leading-edge lithography stages without measurable performance penalty. The constraint is not written into the machine's code. It is expressed in the mass-to-torque ratio of the drive motor, in the field uniformity tolerance of the positioning stage, in the magnet dimensions that fit the mechanical envelope. Change the available material and you change the machine. A data center operator or a lithography equipment manufacturer that cannot access high-purity separated rare earth oxides at scale faces forced substitution, larger motors, weaker field densities, heavier assemblies, or a different drive architecture entirely. The teardowns of current generation cooling hardware show no such substitution has occurred. The magnets are still small, still high field, still neodymium iron boron. The supply chain has not yet broken. The object's physical form is, in that sense, a daily referendum on whether the processing choke point remains open. The dissection reaches its limit at several points that should be named plainly. The 91% processing share figure is drawn from trade flow analysis and industry estimates. It has not been independently audited at the level of individual refinery capacity, and the true figure for specific oxide grades relevant to high-performance magnets may differ from the aggregate. Processing capacity outside China has been growing. The United States, Australia, and Estonia have announced or initiated rare earth separation projects, and some are now operational at meaningful if modest scale. The teardown literature on chip manufacturing equipment is sparse. Most equipment manufacturers treat internal component sourcing as proprietary, and the direct evidence for refinery of origin is thinner than a strong causal claim would require. What the teardowns consistently show is magnet performance consistent with high purity material. They do not show refinery stamps. The inference about origin rests on the convergence of trade flow data with physical performance specifications, not on direct documentation of the supply chain at the magnet level. Substitution timelines, the ramp rate of non-Chinese processing capacity, and the degree to which equipment designers might redesign around different magnet chemistries are all uncertain and contested among analysts. What the sample does show, clearly, is the present condition. The processing concentration is real, its expression in the physical form of the equipment is measurable, and the gap between that condition and the existence of credible alternative processing capacity remains wide enough that it has not yet changed the shape of the magnet on the bench. Taken as a whole, the object on the bench demonstrates something the spec sheet was not designed to communicate: that the performance properties of the magnet are inseparable from the industrial geography that produced its constituent oxides. The restriction did not arrive from outside the object. It was built into the object during refining, before the magnet was pressed, before the motor was assembled, before the cooling unit was shipped. The processing choke point does not appear in the device's supply chain documentation as a vulnerability. It appears in the device's physical design as a capability. The magnets are small and powerful because high-purity separated oxides were available. If they had not been, the devices would be larger, heavier, or architecturally different. Every cut leads back to the same layer, not because the chain was designed this way, but because the chain calcified around the one place that could do the work. The ore is in the ground on 5 continents. The knowledge to turn it into something a data center can use is concentrated in a way that does not move quickly and does not move cheaply and does not move on a policy timeline. That leaves a question worth putting to the next teardown. Which object in your immediate view, a server, a drive, a piece of lab equipment, contains a component whose material history it cannot fully disclose, and what would change about its design if that history were suddenly different? If that question interests you, subscribe. There are more objects on the bench and each one opens differently,